there, this is Group F from ME 2210 with Dr. Rashidi. We're very glad today to present our design for the total hip replacement implant. Stay tuned to the last bit of the video where we present tips on how to protect your hip and prevent it from surgery.
Total hip replacement surgery, also known as hip arthroplasty, involves replacing the damaged sections of the hip joints with artificial parts made of metal, ceramic, and hard plastic to reduce pain and improve function. The prevalence of total hip replacement increases with age, with significant rates observed in older adults. Symptoms indicating the need for hip replacement include persistent pain, limited mobility, difficulty with everyday tasks, and changes in appearance or sound. Manufacturing processes for hip joint prosthesis involves various techniques tailored to the materials used. Materials such as copper chrome, titanium, and stainless steel are typically shaped through forging or investment casting, followed by machining, polishing, and coating. Polishing plays a crucial role in achieving high-grade bearing surfaces, traditionally done manually but now facilitated by advanced lapping and polishing machines. The hip replacement market is significant, valued at USD 7.42 billion in 2022 and expected to reach USD 10.79 billion by 2030, with North America leading in market share. The prevalence of osteoarthritis driving the need for hip replacement surgeries is increasing due to aging populations and government support, benefiting top companies like Johnson & Johnson, Stryker, and Medtronic, among others. Joint biomechanics encompasses various concepts crucial for understanding the mechanics of human joints and their functions. The joint reaction force generated within a joint in response to external forces is vital for maintaining joint stability and function, such as in the hip where it balances body weight and abductor tension to maintain a level pelvis. Coupled forces occur when two movements and associated forces are linked, while joint congruence relates to the fit of articular surfaces with higher congruence increasing joint contact area. Friction and lubrication play essential roles in joint friction, with lubrication reducing friction to minimize wear. Free body analysis involves applying Newton's law and concepts like force, torque, work, and energy to analyze joint mechanics. Clinical implications include actions that decrease or increase joint reaction force, such as modifying component placement in total hip arthroplasty or adjusting patient gait to alleviate joint stress.
This CAD model will showcase the four crucial components of a hip replacement. We begin with the femoral component. That part replaces the upper portion of the thigh bone. It ensures stability and seamless integration with the natural anatomy and allows for optimal weight distribution and movement. Then next up is the acetotubular cup, the hip socket counterpart. This component mimics the function of the natural hip socket, providing a durable and low friction surface for smooth joint movement. It's designed to withstand rigors of daily life and enhance the patient's overall mobility. Now let's talk about the plastic lining over here. These crucial components, often made from materials like ceramic or metal alloys, ensure frictionless articulation between the femoral head and acetotubular cup. And the design minimizes wear and tear, promoting longevity and sustainable functionality. And lastly, we have the stem. That is the anchor connecting the femoral components to the natural bone. And this part plays a pivotal role in maintaining stability and supporting the entire structure. And altogether, these four parts combine to create an assembly like this.
The socket is designed to serve as the new acetabulum. This component is crucial because it is inserted into the pelvic bone, replicating the actual socket part of the hip joint. For this purpose, we have selected a high-grade ceramic material. Ceramics are well known for their long-lasting lifespan and remarkably low wear-out rate. It is scratch-resistant, empowering our design for durability and reliability. Also, ceramics are well tolerated by human bone, providing an excellent surface for bone attachment, and additionally, ceramics are strong enough to support active activities for our patient, accommodating a wide range of movement without compromising the integrity of the implant. Our ceramic sockets are made through powder compaction and sintering, a two-step process perfect for crafting component with strength and precision. First, we mix the ceramic powder uniformly and compact it under high pressure into a mold. This step forms a rough socket surface by intensely packing the powder. Next, the part is sintered, meaning we heat it up just below its melting point. This bonds the ceramic particles, enhancing its strength, durability, and reducing porosity for better wear resistance. The insert component serves as a new cartilage within the socket. We selected polyethylene for this part due to its ability to replicate the smooth, lubricous nature of natural cartilage. This ensures a smooth articulation within the ceramic socket, reducing friction and wear. The recent advancement in the manufacturing of polyethylene, particularly in terms of its molecular weight and cross-linking, have resulted in a material that is far more resistant to wear and deformation. We use injection molding as the material process for the insert. The process starts by melting polyethylene and injecting it under pressure into a precisely shaped mold. This method ensures every nook and cranny is filled, perfectly capturing the design needed for optimal function. As polyethylene cools down, it solidifies into the exact shape and size that we want, resulting in a durable insert with a smooth finish.
The piece that connects to the femur is known as the femoral stem, and the piece that connects to the femoral stem and interfaces with the socket is called the femoral head. The material chosen for these two components is titanium. This is because of three reasons: its strength, cost to manufacture, and its biocompatibility. The metal is sufficiently strong. It's stronger than human bone and will not be a breaking point from day-to-day use, but not too strong to drive up manufacturing costs. It can still be machined or ground, for example. Titanium also has an endurance limit, so fatigue failure will not be an issue for the patient. Lastly, it is biocompatible. Titanium forms a thin titanium oxide layer that resists corrosion inside the human body. Some existing hip replacement designs have the femoral stem as one part. However, this complex shape makes it difficult to manufacture. Splitting this part into two allows one very complex part to become one simple and one irregularly shaped piece. Starting with the femoral head, this part is mostly spherical, and such machining by turning would be the most effective manufacturing process for this component. This type of machining is similar to that of a lathe, where the workpiece is rotated into a cutting tool to shave away the metal. This cutting tool can be automated to remove any labor and increase production rates. Turning allows for quite precise tolerances of less than a millimeter. Next, with the femoral stem, forging would be the best manufacturing process. This will be a two-step process. The first, impression die forging, will shape the end of the stem that goes into the femur, and such the tolerances for this step are not as critical, and such less force can be used. The second impression die forging will create the angle towards the top of the part that interfaces with the femoral head. These pieces can be coated and polished to add another layer of protection in the event that loose titanium from entering the bloodstream.
Thank you for staying until here. That wraps up our research, design for X, material selection, and according manufacturing process for the hip replacement implant. But ideally, who would want a hip made by metal, ceramics, and plastic instead of our own bone? So here's a few tips that we can apply to our daily life to have a healthy hip. First off, posture is crucial, especially for a student. Try to be aware of sitting straight and standing straight to reduce load on the pelvic. And second, stay active by simply moving around after long hours of work. And this stretching method shown in the video is also perfect for releasing stress in the hip. Thank you so much for watching and have a healthy life.